An autonomous drone surveying an industrial facility encounters shifting shadows. It misinterprets the data, spins out of control, and accelerates straight into a wall. Generative AI failures carry strict real-world consequences. Lawyers have faced severe sanctions for filing official briefs containing AI-fabricated legal cases, and autonomous enterprise agents have leaked data after processing compromised inputs. Standard industry consensus treats these events as temporary software bugs. The prevailing assumption is that these errors will inevitably disappear once we apply larger datasets, utilize heavier compute, and more rigorous reinforcement learning. Treating these failures as solvable coding errors is a category mistake. Many of these breakdowns are the mathematical consequences of the exact statistical mechanisms that give large language models their power. To evaluate these systems accurately, we have to map their failures across a specific spectrum, starting from a temporary engineering hurdle on the left to a permanent structural boundary on the right. Differentiating a fixable error from a permanent limit dictates how product managers and engineers must build. Deploying AI safely requires knowing exactly where the boundaries of the architecture actually lie. We begin with hallucination. Generating a confident, fluent falsehood is not a system malfunction. It is the model functioning exactly as designed under its primary training objective. This diagram illustrates the next token objective. When evaluating continuations, the model optimizes strictly for statistical plausibility. An obscure true fact registers a 2% probability, while a fluent fabrication scores 89%. Lacking an internal fact-checker, the loss function accurately selects the highly probable fabrication. Alignment techniques like reinforcement learning from human feedback can actually worsen this dynamic. By rewarding models for being helpful and conversational, alignment trains them to be excessively confident and agreeable, leading directly to sycophancy. Enterprise deployments attempt to bypass this with retrieval augmented generation, or RAG. This technique forces the model to consult grounded external documents, effectively providing a reference sheet before the model begins generating text. RAG reduces error, but the underlying neural engine still generates text based on statistical token probabilities rather than true comprehension. The architecture remains entirely probabilistic. As long as the core system relies on ungrounded statistical generation, a residual rate of confident error is hardwired into the output. It cannot be entirely eliminated by engineering patches. This reliance on statistical patterns introduces another severe vulnerability: a lack of robustness. Robustness measures a model's ability to maintain performance under stress, unusual input distributions, or direct adversarial attack. The most common adversarial attack is a jailbreak. Attackers use carefully optimized text suffixes that mathematically calculate a path around a model's safety training, forcing it to output refused content. Alignment guardrails operate as statistical tendencies, not airtight software locks. A sufficiently clever input sequence will always find a probability path around them. This chart shows prompt injection. In an agent, top-level system instructions sit above external web data. An attacker hides malicious text inside a web page mimicking those instructions, hijacking execution. Processed as a flat token sequence, the model cannot separate trusted instructions from untrusted context. Even without malicious actors, models suffer from distribution shift. When a deployed model encounters inputs that deviate from standard internet training data, like regional dialects or code switching, performance degrades sharply. Slight, completely innocuous rephrasings of a basic prompt can result in wildly different answers. These security vulnerabilities exist because the model relies heavily on superficial statistical patterns to generate text, rather than utilizing a robust structural comprehension of the tasks it is executing. Because models are statistical reflections of their training text, they absorb the historical, social, and cultural biases present in that data, amplifying them at scale. This creates two distinct categories of harm: allocative harms, where a model unfairly distributes opportunities in automated hiring or lending, and representational harms, where models generate stereotyped or demeaning depictions. Bias cannot be technically solved, as fairness definitions contradict. This graph plots demographic parity against equalized odds. Adjusting the model to reach an optimal threshold for one metric violently destabilizes the other. Balancing them requires human judgment, meaning technical teams make social policy decisions. The data ingestion process also creates the problem of memorization. Models frequently overfit to specific training examples, allowing bad actors to extract verbatim personally identifiable information or copyrighted intellectual property. Mitigating this requires rigorous data deduplication, but that creates a direct conflict with model capability. High performance requires memorizing a high density of factual information. Data ingestion failures represent an inherent tension. You cannot infinitely scale a model's capabilities without pressing up against regulatory privacy laws and complex social fairness limits. Beyond data and bias lies the deepest unresolved limitation in generative AI, the multi-step reasoning gap. Looking at this split-screen UI, we see the jagged competence profile. On the left, the model successfully generates highly complex Python code for logic puzzles. On the right, the exact same architecture fails a basic arithmetic variation of that prompt. This jagged competence fuels the stochastic parrot debate. Researchers are sharply divided on whether these models possess an internal world model or if they are sophisticated pattern matchers that mistake surface fluency for actual understanding. Techniques like chain-of-thought prompting and dedicated reasoning models artificially improve multi-step planning by breaking complex tasks down into intermediate tokens, forcing the model to show its work. Chain-of-thought demonstrably improves benchmark performance. However, it does not settle the philosophical question of whether the system is genuinely reasoning or just executing a much longer, highly localized pattern match. If impressive fluency merely masks a lack of deeper comprehension, achieving reliable logical reasoning may require entirely new architectural innovations beyond scaling up current methods. We can now return to the core question: where do these failures sit on the spectrum? Issues like data memorization and basic robustness drop into the left side as mitigable engineering hurdles. Bias sits firmly in the center, manageable through curation, but requiring continuous human judgment. But zero hallucination generation, flawless prompt injection defense, and reliable reasoning cluster on the far right. They press against the structural boundaries of statistical token prediction. The actual trajectory of generative AI lies in this specific distribution, somewhere between uncritical hype and reflexive dismissal. For product managers and developers, the operational reality is strict. High-stakes applications must explicitly design around these structural limits. That means requiring external citations, isolating agent environments, and keeping human oversight tightly in the loop. Intellectual honesty demands evaluating system limitations with the exact same rigor as capabilities. A technological deployment is only as safe, reliable, and powerful as our understanding of exactly how it breaks.